All right, everyone. Well, let's continue our discussion and investigate wave packets. Well, we've drawn pictures of wave packets, but how do we represent them mathematically? And in particular, how do we build up a wave packet out of, say, sinusoidal functions? Well, that's done with a trick called Fourier synthesis. And here, I want to talk about that now. Okay, the question before us is, how do we describe non-harmonic waves like wave packets? Okay, things like that. Well, one way to do this is to construct them out of harmonic waves. In fact, all non-harmonic waves can be built out of harmonic waves. That is, they can be built out of sine and cosine functions. Okay? You may have heard of this, all right? Mathematically, we can state that any function, well, here, let me write it out. Any function that's defined over some region of space, excuse me, let's say from x equals minus L over 2 to plus L over 2, can be written as the sum of a series of harmonic functions, so-called Fourier series, after the person who first worked this out. Okay? I'm going to write down the expression for the series now. I want you to have a look at it. But we won't actually be working mathematically with the Fourier series very much. We're mostly going to investigate this qualitatively. In any event, here we have, for each frequency, we have a cosine wave of that frequency times a coefficient, telling us how much that particular frequency contributes. Like so. We have a sum of sine and cosine functions. Where the different frequencies are given like this, n pi over L. It turns out you need only certain discrete frequencies to build up any periodic function or any function defined over a limited region. All right? And as I mentioned, although it's not too hard to work this out, we're not going to limit ourselves to a qualitative picture here. And so I want to show you a simulation which illustrates what we've just said. Okay, here's a applet from Paul Falstad, which illustrates Fourier series. I really like it. You should go have a look at it too, whenever you like. Maybe we'll do this in class. In any event, we can consider any different function and show how it can be built up out of sine and cosine functions. To begin with, here's a sine wave, all right? Well, that's pretty straightforward. You can see that we can, of course, build that up out of a single sine wave, right? We could, if we consider this as a signal in time, we could play the signal on the speaker, like so. That's great. But now let's look at a non-harmonic function, perhaps a square wave. You can see that the sine wave is not a very good approximation to the square wave, but it turns out we can build up a square wave out of harmonic functions. I'm going to do that now, and I'm also going to turn on the sound so you can hear the different frequencies as they're added. So far, we've added a few terms, and we already have a pretty good approximation of the square wave. If we keep adding terms with the right amplitudes, we can get almost a perfect representation of the sound wave, of the square wave, rather. All right? So we can build up a non-harmonic function like a square wave out of harmonic functions, out of sine functions. Here's another one. Pretty neat, right? This app lets you do some fun things. For example, you can draw your own function and then fit that. Something you might do if you investigate this. All right? In any event, the point of this simulation is to show that you can build up any non-harmonic function from harmonic functions. All right? Here, let's pause for a second. Okay, I have a second simulation to show you as well. This simulation shows the frequency spectrum, that is, the amplitude as a function of frequency of the different sinusoidal waves that we're going to add, needed to construct different types of wave packets. Here, I'm going to start the simulation. Right now, we're constructing a Gaussian wave packet that has a very long length. And you can see that in order to do this, we just need to use a narrow band of frequency components around the center frequency of this waveform. I can, but watch what happens as I make the width of the wave packet shorter. Can you see what's happening? As the wave packet gets shorter, the spectrum gets broader. That is, a short wave packet is composed of many, many, many different frequencies over a wide span, whereas a long wave packet is composed of a narrow band. An infinitely long wave packet would be composed of a single sinusoidal function. All right? Notice that if I change the center frequency of the pulse, it changes the position of the center of the spectrum, but it doesn't change its width. Like so. So every wave packet, everything that looks like this, can be considered to be built out of sinusoidal waves of definite frequency. But there's a range of frequencies that go into this wave packet. We can't say that the wave packet has a well-defined frequency. If you like, there's an uncertainty in the frequency of some width, which is the width of the band of frequencies that we had to add together to construct this wave packet. Here, let me stop that. Actually, one more thing I should just say very clearly. Notice here that we can see the classical version of the uncertainty principle, the time bandwidth product at work. When we make the width of the pulse shorter, oops, When we make the width of the pulse shorter, the width of the spectrum gets wider. The uncertainty in frequency grows as the uncertainty in time gets smaller, and vice versa. Okay? Okay. Now let's stop this video, okay?